Okay, I'd like to do one more exercise for the gas problem, and then we're through with it. I want you to kind of have a little more appreciation for the Qmax over G sub I ratio. You know, that you, don't get bogged down with the idea that it's got to be permeability contrast. That's how I run into this problem continuously, and so I worked out a little exercise or example, you know, where I don't have anything there. Where I'm going to use max, but you keep everything, you know, consistent. Ratio. Layer 2, the more permeable layer, the less permeable layer. Always in that order. And R, or the ratio, is equal to, we're going to put it in terms of reservoir variables. You know, we gave this before. You know, this is what the reservoir characterization or the reservoir simulation people have a tendency to look at these ratios, and they call it the speed of the layer, which is nothing more than this. In fact, if you take the Qmax over G sub I, in the gas industry we used to have a way of setting the allowable for a given field, and it was called the rate of take. And you divide the gas in place by the initial rate, and that would give you a rate of take. Actually, if you do that, that'd give you time. It gives you time, so that you can see in terms of that if we're given gas in place, if you would produce a certain rate, if it never went on decline, it would last exactly that many years. Okay, so it's a way of looking at this thing in terms of time. Let's look at the problem where we're going to set this equal to 10, okay? Let's assume for simplicity that the perms are equal, the porosities are equal, the skins are equal. I can get there by a volume ratio other than a permeability ratio, okay? You know, so if I want to ignore the log approximation, make sure I keep it straight. Now I can end up where you know, if the Qmaxes are the same, it's going to be basically a ratio of G sub I. G2 over G1 equal 10 is equal to RE2 squared. You forget, this is in a log term. Ignore the log approximation and just see what it would take to get there. You set this radius equal to 10, and go ahead and set one radius equal to value, and what would the other radius have to be? And I think I ended up setting running a little bit of problem about what's the high perm layer and what's the low perm layer when you assume the permeabilities are equal. So go ahead and set one radius equal to 2,000 feet, and what radius would you have to have in order to get a ratio of 10? Remember, you can't pick up the volume in, we assume phase are equal. You can't pick it up in H because this is really a KH over a KH, and we want the deliverabilities to be equal, or the Q sub i's to be equal. So the only place you can pick up the volume is in terms of your radius. A second part of the problem would be, let's assume the radiuses are equal, the K's are equal, and the porosities are equal. What values of skins do I have to have on each layer? To get a ratio of 10, okay? And the example I ended up setting up if S2 is equal to 0, what is the S1 when the K, phi, R sub E now are equal to each other, okay? And I also ran one if S1 equals 0. And I also looked at a problem where if S2 is equal to minus 4. And then if S2 is equal to plus 50, okay? You see what you have to get in terms of the skin of the other layers on this part of the problem for the ratio to stay 10. Everything else is equal. Permeability, the porosity, your thickness, and R sub E. Now, I just want you to get a feel that you can vary all of these numbers in some fashion and still end up with a 10 ratio. Like permeability ratio could only be 2 or 3. But the skins could be different, and the volumes can be different. You can still end up with a 10 ratio. The other radius I got to get a volume ratio was 632 feet. Okay? The basic point is to demonstrate to you that you can get the same type of differential depletion, everything else being equal. And that you can sketch a reservoir system, because deltaic reservoirs and all that type of stuff. I can have a system like that, alluvial fans or what have you, where this is going to be in this case here, you calculated 632 feet. This R is going to be equal to 2,000 feet. Okay? And they say, well, this is one well problem again. Well, I can set this equal to 100,000 feet, and this would be a field problem now. All right? But the characteristic, the important thing of this type of system, and if you go and read the literature on these types of reservoirs, They demonstrate that there are seals between these things, and it requires no cross flow to get the behavior. You know, the differential depletion. And if you take this type system, you know, we just took our problem that we just solved, and we went to program 7151, and we input, we took the sum of the two Q's, the QI's that you had, we add them together, divide by 2. Okay, so we made Q1 equal Q2. Then we added the gas in place together, and we got a ratio of 1 to 10. And this is what the P over Z would look like. You know, this is the differential depletion that you'd get for a system where QI1, QI2 is equal. And everything's coming into the volume, and you're sure enough you're going to see differential depletion, and the distance from here to here and here to here is the 10 to 1 again. QI equal 1 equal QI1 equal QI2, K's equal, H equal, porosities equal, skins equal. Everything equal, but I still can get differential depletion because my volumes weren't. And like that sketch, you try to make the point, you know, that, well, you say that's a one-well type of system. It don't have to be one. It could be a total field. You know, this could be the radius of the lower reservoir, and this would be the radius of the upper reservoir. And look at some of the geologic pictures, and you'll see where they sketch some of the fan deposits that way. You know, the early ones are were thicker and on the bottom, and then as you come up, they'll get smaller. But in between, there's always kind of like a geologic break in between, and that's where your shell barriers come in. RFTs, no cross flow. It requires a no cross flow to get that. What'd you get for these skins? For the first one, where S2 is equal to 0, what did you get for S1? I got a minus 7.2. Okay, if I had a 0 skin on a low perm layer and a minus 7 on the high perm layer, everything else would be equal. R sub E, the skins, the K's, the H's, and the P's, but I'm going to get a 10 to 1 ratio, and I'm going to have differential depletion. Look at what's happening. You've increased the ability of the high perm layer to really produce fast as anything, and that's what's really causing with a differential type depletion. The other one's slower. This layer is going to be faster. It's the same thing with the next one. If the high perm layer's got a 0 skin, the low perm layer has I end up getting a plus 72. Have you seen one that high before? Possibly. You know, but if you had that condition, this is exactly what could you do to eliminate differential depletion? You stimulate that layer. And I guess for the S equal minus 4, S2 equal minus 4, S1 would have to be equal to minus 7.6. And then I ended up with if S2 equal plus 50, S1 only has to be equal to minus 2.2. Not bad. You know, these aren't unreasonable combinations. There's a copy of a paper in there, the Oil and Gas Journal, I think it was published in 1987, where a fella was analyzing abnormal behavior of a gas well with a P over Z, the curvature, and it was shut in for 4 years, and it built up and all types of stuff. And go in there and see some of the numbers he used to get a match. And remember the Q max over G sub I ratio, because he ended up, I think, one layer, he made the permeabilities equal for the layers, and I think the thickness were reasonable equal, but he had one layer in his model, it was a model study, it had to be a plus 150. You know, that's awful big. But looking at this equation, you can take that same problem, and how could you move those numbers about? The K's a little bit and the skins a little bit in order to get the same ratio that he got. We'll go in that article, see what kind of ratio that you would calculate using his numbers for his history match. it's interesting to take some of this material like this and go to a publication and see how you'd solve it now differently, or how you'd solve the problem a lot quicker. He ended up only being able to solve his problem on a model. You could calculate, or you could solve it on the back of an envelope. You'll also see in there where when he shut in his model, when he shut in the system for about 4 years, there was backflow occurring during that entire 4-year period from the high pressure low perm layer into the more depleted high perm layer. And then when he brought it back, the well back on production in 4 or 5 years, even though it was shut in surface, you were injecting gas into the other over that entire period of time, and there was a big spike of production, which is exactly what you should expect. So you can see, you potentially can see big spikes of increase by changing the back pressure on the system too, because you're producing all the gas out of the high perm layer over a short period of time, and it might look like a transient spike. But if the permeability levels are such they're too high, you know it's layered no cross flow. And then we'll do infill drilling. This is going to take too much time on here, but we did do the case. We ran a case, and we ran it with 7151 for the gas. And all I'm going to do here is show you what we ended up getting as the result of running going from 640 to 320 to 160 acres, and this is what we ended up with. You can see there's a rate versus time. The high perm layer is down here at the base. The low perm layer is the upper one, and then the sum of the two results in it. So you can see just even going from 1 well to 2, you get to 4, you even get a higher peak after you go from, you do the infill drilling where you've gone from 2 wells to 4 wells, and that's just the result number of wells. You can also see the main contribution of everything is coming in from really the low perm layer. The high perm layer is virtually depleted. That's more so in on a liquid solution that we're going to get to do next. And I'd ask Beige to get me copies of the worksheets that I did by hand over here. And so I did do the problem by hand. It'll be easier if I can. To minimize reservoir interference, the best thing I can do is to develop the field on equal spacing. So how is that going to enter the problem? It turns out that if I develop on a cluster, I in essence have a system where a well near the apex in a triangular system, and if you look at the shape factors in the pressure transient analysis book, or if you look here in this book, there's a copy of a bunch of papers of mine. There's an example in there where, I don't know, it was Vinot and I worked on, it was the Big Dotty field in the UK Hewitt. If somebody wanted to know what difference would it make if we drill another well in the field. So we looked at it in this light, and it says that the only way the location of a well in the field enters into the problem is an equivalent skin. That's all. If you've got 8 wells in the field and they're approximately the same, every well is going to drain 1/8 of the total volume. Whether the volume is a triangle, square, rectangle, it really makes no difference. A volume is a volume is a volume, okay? You have to kind of appreciate. So the only place that the well, being not in the center, enters in the problem is in basically a skin effect. And if you look at the various shape factor skins in the paper, you'll find out about the worst that you could do for this type system is have about a plus, I think, 3.8, or let's say approximately a +4. So you just put in a pseudo-radial flow equation, and you've included that effect in your forecast. And then you say, well, I'll look at the problem the same problem and locate them all exactly equal and so on and so forth, and I've eliminated reservoir interference, you can put a zero skin in for that, run the same problem. How much difference does it make? But remember, this is bottom hole. By the time you come through a tubing size, which you may be limited because of depth and diameter, by the time you get to wellhead, it has zero significance, okay? You can solve the problem, again, on the back of an envelope. What's the effect of interference? So we're talking about interference here. I've included it here in this problem, even though if this was a section in a total field and they were all drilled in the same location, then they would all be about in the center of their drainage volume. But I'm going to leave it like with a corner, or it's in a corner. And if you look at those, let me find the page, because we need to do a little more than just talk about it. There's a paper in here, a very short paper. I don't even remember the title. Uh, 206. The shape factor C sub A expressed as the skin. And if you go to this table, there are a couple of surprising things. Look for the shape factor of a well over in that northeast quarter, and you come down here referencing to circle. The skin is plus 0.973. Okay, so what we're going to do in the pseudo-radial flow equation here is we're going to add a skin, a shape factor skin, into the problem. Okay? This is to get you to think about the idea of interference and how you would handle a well not in the center of a square. You don't have to go to a rigorous analytic solution. I was real surprised, and this is another of those examples. When you work something by hand, you run into some surprises. You can see from the next figure below, now we're going to have a well on 320 acres. That's why I had to locate it up in the northeast quarter. When I come down to a 20-acre spacing, I've got a symmetrical system there. One in the lower part, one in the upper part. And we'll look for that one. And see what the shape factor skin is. It's the second column, the second one down. Plus 0.973. I was real surprised that this oddball shape would end up to give the same shape factor skin to use in the problem. Okay, the next phase then would be to go, that's going to be phase one. We're going to go to 2 wells on the 20-acre spacing. We're going to assume the original well has a zero skin in the low perm layer. And the infill wells, you see, this is what you have to remember when you're reading these papers. That, they're comparing something before infill drilling, and if you read a lot of these papers, you find that carbonate wells, the wells were completed open hole and shot with nitroglycerin, okay? They really weren't stimulated and diverted. So some of the increase that is being picked up as a result of drilling an infill well is because they're actually doing a better completion job on the new well than the old. But when you look at one of these figures, you're attributing all to areal heterogeneity, see? Follow? So the infill well, we're going to have a -4 skin on both layers. And again, I even have, surprisingly, that I was real surprised that a well in that system I thought would have a lot worse skin than a well in this system turned out to be the same. And we're going to complete the well only, or the completion in a high K layer is not necessary when you look at the rate time. What we're going to do in order to make sure we get through the whole thing is, you're not going to have to do it. I did it. All the worksheets are here. Let's just go through it. You work through the one. Let's just kind of try and develop the concepts here where you won't have to work it out by hand. Okay, then we're going to go down and we're going to do a phase 2. We're going to drill an additional 2 infill wells. We're going to go to 10-acre spacing, but now we have a well in the center of a square and the shape factor is going to be 0.
What about completion on that one? Only the high K layer on that one?
Only the low K. Actually, we're never going to complete in the high K again. When you look at the rate time, you'll see why. There's nothing there. And then let's say because it was so high K, you might have water move in. You drilled a new well and logged it, and when you log it, you saw that that layer was wet. Okay, so you don't even perforate and complete. So you perforate and complete in the low perm layer, and voila, you're going to end up with a 700-pound shut-in pressure in a new well versus the other one of 200 pounds. And what are you going to conclude? Aerial heterogeneity again, isn't it? Pods. There's all kind of pods out there. Look, I got 700 pounds and the other well's only got 200. See, this is, when you start to put all these things together, you can start to unravel some of this supposed aerial heterogeneity and proof with examples that look, if you look at it from this light, you start to have lots of questions. It's not to say you can't have aerial heterogeneity, okay? But I'm saying the layering, no cross flow, is an order of magnitude more important than the other, and that you can explain many of the examples strictly by layering. That's all. That's the only concept that I'm trying to develop here. Okay. And the properties that I set out here really are properties that I came up with by reading all of these papers on the water flooding in the carbonates in West Texas. These are very typical values of 20 millidarcy in the high perm layer, about 2 millidarcy in the low, with thickness in the high perm about 62 feet, thickness in the low perm is 312 feet, and that's going to give me a high B value. The pseudo-steady state equation in terms of permeability in darcies now, with 708 is gives you permeability in darcies. And then we have a skin. Initial pressure 1,000 pounds, the flowing pressure 100. The hydrocarbon porosity about 20%. The total compressibility 27 times 10 to the minus 6. And remember, we're not dealing with original gas in place now. It's the expandable oil in place to whatever pressure. You know, I could do this either way because the flowing pressure is going to cancel out of the ratio when I deal the ratio. You know, so I can do either way. But here, NPI is the total amount of expandable oil that would occur in a reservoir if I were to take it times shut-in pressure times a 0 pressure, okay? That gives me NPI. I'm going to use an oil viscosity of 5 centipoise. You'll find that in some of these field case histories. And I'm trying to demonstrate by this figure what we did before, that the Q has got to be, or there's a stabilized back pressure curve for a single phase liquid too, except you're not plotting a shut-in pressure squared minus flowing pressure squared. It's the shut-in minus the flowing, and this is the old classic definition of productivity index. Versus Q, log, or Cartesian has an N of 1. The pressure versus the cum, just like gas, you know. in a sense, you've worked this problem before, so there's no use to go through all with the mechanics, particularly when you've got it documented. And you've got an NPI either at the final flowing pressure, 100 pounds, or you can define it in terms of a zero. You go either way on this problem, just as long as you keep it clear in your head, okay? All right, these are going to be, this is the basic flow equations. It's a lot easier to solve because you have the Q at any time is equal Q sub I divided by E to the D sub I, which is nothing more. Over here, since the pressure appears in both places, the flowing pressure appears in both places, you don't have to worry about it, just as long as you're consistent in the ratio, using it either the flowing pressure or zero. So you could use the Q max over NPI. And if you want to do it in years, you just include the 365. Over here to the right, I show where the original case, in terms of well, just QI has QI over the ratio 1 minus PWF for PR bar. This is rigorous. If you go back and read the original decline curve equation paper, this is in there. And if you go back and read a simplified approach to water influx calculations, it's in the appendix there. It's the single phase liquid solution, where QI max now is equal to QI divided by 1 minus the PWF over PI, or the Q max PWF equals 0. Again, stay consistent. Recall that NPI is to PWF equals 0. And for the Kuhn time equation, now this is for liquids that are gas, it's in this form. NP, the cumulative production over any time with respect to the initial is equal to quantity 1 minus PWF over PI times the quantity 1 minus E to this QI over the D sub I times T. For pressure versus Kuhn, it just the shedding pressure at any time is equal to the initial minus see the analogy between gas? Everything is exactly analogous, and everything you understand about gas, you can understand about oil. You can work back and forth. That you don't need special equations and special forms for gas and special equations and special forms for oil. The concepts are identical. You don't have to make a big transition. And PI is equal to 1 minus NP over NPI. So for a 40-acre case, we're going to calculate the QI of the more permeable layer. RCB would be 745 feet, 1,000 minus 100. There's the shape factor skin, and then we have a plus skin in here. For the more permeable layer, the QI1 is 197 barrel oil per day for a skin of minus 2. Or it's going to be 149 barrels oil per day for a skin of 0. I'm going to show you, I'm going to make both forecasts, okay, and just kind of demonstrate to you that it just doesn't make that much difference on that high perm layer. And the smaller volume. Remember, our volume is 1 to 5 now. That all enters with a picture. So for NPI 1, this is nothing more than the in-place 79,975 stock tank barrels. For layer 2, now we're going to have a 0 skin on that one because it was completed open hole, commingled, either acidized with a commingled acid job, or they shot nitroglycerin. When you read these papers, you'll see this is the way they completed all the wells. And these are the fields they went into later and said, let's do infill drilling. So you have to see where things were starting from. And so I calculate the QI of number 2 Layer 2, the less permeable, for an S equals 0, it'd be 75. For an S equal, I think this ends up to be -4. It's 146 barrel oil per day, and there's the NPI. Okay, so we're all set up to start doing the forecast. Any questions? Okay, this is the forecast that was generated for the 40-acre case, one well on section. You can see the numbers for layer 1, layer 2, the -2, and the 0 for layer 1. On the skin for layer 2, the 0. And I've also, in this example, tried to show the same thing again. You know, let's the cross-flow case, S equals 0, you both layers. You can say, well, why'd you do that? Well, when you look down here, look at the production rate for the permeable layer with a -2 or 0. Look at the end of the first year. For practical purposes, there isn't any difference, okay? That layer is gone. It's really gone after about 3 or 4 years. There really isn't anything very much left there. Layer 2 in S equals 0. The reason I did a -2 was just for comparison purposes. You know, if you want to take a look at it. No, this is the commingled -2. This is layer 1. So this is with an S equals 0. That's the forecast. Yeah, so I'm going to add where I stimulated with a -2. This rate plus this rate here, and this is going to give me the total. I've added in, like I tried to suggest earlier, the 0 time so I can have a reference point on these initial rates. You see at the end of the first year, whether I have a -2 or 0, I'm really looking at basically the same forecast. So it isn't very sensitive to that skin. You might say, well, you picked these numbers to doctor up the results. I didn't. And with a commingled rate for was 0 on each layer, 140, 97, 75, 62, so on and so forth. And we did just exactly what we did earlier. Well, let's assume cross-flow. You add the two rates, the S equals 0. This is going to be the 149 plus the 75 is that total, which is here. You know, these are going to be the same. They start out the same place, whether I have no cross-flow or cross-flow. And you can see, again, the difference. After the first year, the commingle is producing 140. The cross-flow is producing 185. I don't know if you can see that as an 8 on your copy or not. 185, 153 versus 97, 127 versus 75. This is an example where this would be true exponential decline, and this would be a b-value about 0.6. You know, so again, we're trying to demonstrate here the difference in the forecast between exponential and hyperbolic, that the exponential is optimistic, in the difference between cross-flow and no cross-flow. Okay, any questions, any problems, any comments? You know, it took me a long time working out this problem. One of the things was just keep things straight. The cumes and reinitializing the problem after 5 years. In each layer, I've got to determine the cume, and I end up with a new NPI when I'm going to do the infill drilling. But I've got to split the volume now, because the original low perm layer's got a 0 skin and the new one has a -4. Now we've got to determine, that's where the interference comes into play. Every well produces volume in proportion to its producing rate. So the new one is going to have, going to drain a proportionally larger volume. And this projection here, the difference between, this is the original well as it would have produced if there was only one well. That's that example in that paper on 9 fields, Oklahoma, Texas, and Illinois. This is the volume that that well would have drained, or is draining. It's the original same well, but now I have another well in it, so it's taking away the volume that it would have had it produced alone. And they call that interference, and that's what this calculation does for you when you proportion out the volume for each well in the same layer. That's interference. That's the volume now that is being produced by the other well. Drainage radiuses have now shifted, and that should be that is in the calculations here. Okay, at the end of 5 years, we found out that the delta P is 284 pounds in layer 2, or the layer pressure is 716 pounds. In layer 1, at the same time in 5 years, this pressure is only 120. It's virtually gone. You can go through here and calculate what the Q2 would be with a -4 skin. Remember, now we're starting over again because we now have 716 pounds. We've depleted it that far down after 5 years. And we're still flowing against 100 pounds. Now we have a -4 skin, though, on this new well because we've drilled it, cased it, perforated, and individually stimulated it. The original well still has 0. This is so the comparison. The new well, completed only in the low perm layer, is going to produce 110 barrels of oil per day against 100-pound back pressure. And the original well still has a 0 skin. We haven't figured out what's going on yet. And you go back and read these papers, they didn't go back and re-stimulate the original wells. It'd be producing only 54 barrels of oil a day. So you end up, the new well is 110, the old well is 54. I add them together to get a total, or 67% of the oil remaining at that time is going to be drained by the new well. 33% by the other well. Does everybody see that? And that's this interference effect that you're talking about. The old well would have you produced along here. If the other well was never drilled, this is what it would have produced. And that's what's being measured in the field. On the original well, it has got a rate time performance. You drill the infill well, its production is going to drop. Because the new well is actually draining from that original drainage volume. A very simple concept. It shows up in several places in literature, but a lot of people really don't grasp it. At pseudo-steady state, every well drains a volume in proportion to its rate. So you just take the sum of all tabulate all the rates of all the wells in the field and the total, and normalize to get a percentage, and if you have a total oil in place, each one's going to be getting that percentage. And you draw no flow boundaries between each well based on the Q's of opposite wells. You look at them and say, well, this one's going to have a shape factor such it'll have a +1 shape factor skin, this is going to have a 0, and so on and so on. That's the way that it enters into the problem. It's just in the back pressure equation. It never enters into the volume, other than you proportion the volume this way. So this is the interference effect. And in the 1 year, this is what the more permeable layer looks like. Like I say here, it's 120 pounds versus 716 pounds. And when we drill the infill well, we don't complete in the lower layer anyway. for a lot of good reason, there isn't anything there. You just suck it away. It would be the so-called thief zone if you commingle it, not even. I hope these are all in order. The end of 5 years T equals 0 for these forecasts. So now I'm going to go ahead and make forecasts for the original well and the new well in the low perm layer, and that's what I've generated here. These are the forecasts. There's the original well at 5 years, but on my calculations that's going to be T equals 0. You know, I'm reinitializing the problem. Well, the new well is producing 106, the old well 55. The layer 2 well with the infill well, the -4, has got 161 at T equals 0 and 108, I guess, with an S equals 0. The reason I did that, I've got a plot, is what if I would have assumed an S equals 0 of the infill well? I've got that, and I can include that on my plot. Okay. Because that question is going to be asked: how much really of that spike or increase in production is due to you making an assumption that I'm going to have a -4 skin? So this is attempting to answer that question, and I've got it on my plot here. I'll try and put it on up here on a board for approximately the scale, and then we might see if we can. I don't know how easy this is going to be to get to reproduce this Cartesian plot, but we ought to see if we can't maybe get a Mylar or a transparency, and then you darken the lines and then make a copy for everybody so they don't have to go through all the plotting. But I'll pass it around after we get through the discussion. You can see what it looks like, and then you can compare it to some of these plots that have been published in the literature. You know, so that's why, even though I said I was going to use a -4, I said, well, somebody's going to ask how much of that total is really due to stimulation by itself. So I just went ahead and made that calculation. I was anticipating you people. You know, say, well, he's reading this problem. What if? It was real hard keeping all this straight. But again, it's worth it in terms of trying to figure out the logic. Just like when you go through this exercise and do this with regard to interference, you start to understand what that means. I'm sure every one of you read in literature something about, well, another well is drilled, it causes interference. What does it mean? This translates it directly into rate. I really don't care about interference pressure. What does it do to my rate? I have to convert it to rate. It gets back again to what we were saying earlier. You can do all kind of pressure transient analysis, generate numbers. It's garbage if you don't convert it into a production forecast. It's exactly how interference translates into rate versus time. It means absolutely nothing in terms of, well, I have a 10-pound drop because we drilled this well over there a quarter section away. How much did it cost my production? You can calculate it. Here we're going to drill 2 more infill wells at year 10 to get a 10-acre spacing for a total of 4 completions in a low perm layer 2, and we still have 1 completion in the high perm. You saw earlier, we're going after 3 or 4 years. No reason to complete there. It may have even watered out. and we're going to calculate NP to year 10 for original and the first infill well to get a new PR bar. And I'm just trying to keep track here of the original oil of 399,876, the cum that I had at year 5, and then the remaining NPI. With a 286403, and we just continue down, always updating the QI and the NPI. And the shut-in pressure, okay? You're just kind of keeping track of things. As a result of the new production, there's a 430-pound drop. Now we're down to 286 PSI. With cumulative production for the infill well, we're just going to go through here. You keep track of the original, the first 5 years, in the next 5 years, you have to end up how much is remaining any given time. And I think here it's going to be 287 pounds. Here we're going to calculate the rates for original well and the 3 infill wells. Let's soon, I finally realized that we ought to go back and re-stimulate that old well just to make the calculations easier. Now I can calculate one well multiplied by 4, end up what the 4 infill wells are going to look like. I'll get the Qmax, NPI, and I can continue my calculations. The final piece of material is the production forecast for 10-acre spacing. We got -4 skins on all 4 wells. That's the rate versus time that you end up with. So then the final plot, and I'm going to pass it around first. You can take a look at it, and then we might see if we can't take this and get a darker copy, or maybe try and shoot a copy and then we can darken it in by hand and have something that we can copy for everybody. You have to remember, again, these illustrations in the papers are on Cartesian too, and this is Cartesian so we can compare it. But let me sort of show you what I've got here the best I can. This is the original well. This is what it would have done had no infill well been drilled, some of the 2 layers. When I drilled the first infill well, this is the result of the interference. That well actually exists, and this is the way it'll drop off continued production. You go out there and measure it from that well, so it's going to look like it dropped. This is a result of just drilling the 1 infill well in a low perm layer. It spikes way up to here, okay? Then it starts to decay, and this is where we drilled the next 2 infill wells, and this spike is even higher than this one. And again, we've added 2 more wells. This is all because there's a lot of oil or reserves left in the low perm layer. Has nothing to do with the high perm. So you see it coming down, big spike, coming down a even higher spike after we drill the other 2, then it starts to decay and come down here. I mentioned earlier this would be the infill well. The first infill well by itself, if we didn't include the effect of a -4 skin on a new well, would have come up here and kind of decayed, and then we could have redone it. But you can see approximately what it looks like as a result of taking a 2-layered system, a large low permeability volume that wasn't stimulated, and then go back and look and see what some of the figures look like in papers that were reported as this is a result of infill drilling due to aerial heterogeneity. And of course the aerial heterogeneity in this problem is 0. It's uniform in both layers, and you can see you can get the same type of response with a layered no crossflow system by doing infill drilling. And all that does is raise the question. That doesn't say that there isn't aerial heterogeneity, okay, that you're not going to get some. But I'm wondering how much. is really due to layered no crossflow and how much is due to aerial heterogeneity. And then the original wells. Look at the cases and always go back and look, how are the original wells completed, as opposed to the new ones that are drilled and cased, perforated, and stimulated. And you'll find some of the better operators individually stimulate the layers, not only for the producing wells, but for the injection wells too. So if we can get somebody to volunteer to try and take this figure and enhance it so we can make a copy for everybody. Okay? I appreciate it. And with the fact that we worked that other one through in such detail, I don't think there is the necessity of working this one through. You know, it's just going to be repetitive. And you can see the concept, or you've already been introduced to the concepts earlier, and you could follow this real easy now, I think, how we did it. But you could also see methodically how you could set this up, and you have to kind of keep track of things. It's real easy to do. And then you see, I spent my first 10 years in the gas department, which was great. I worked with the single-phase flow. And I spent my next 10 years in the computing department. And I developed a general purpose reservoir engineering and production engineering program. And before I ever wrote a general purpose computer program, I always solved a problem by hand. You know, and that's what this is. It really starts to give you the insight into what's going on. And you at least have a test problem to run after you get it built. You know, at the end of the development of any program, it's is it the analyst's fault that it don't run, or is it the programmer's fault that it don't run, or the coding? But that's all I've got to say, other than we're going to try and enhance this plot that goes with this table. And if you have any questions or any comments, you ought to pick up these papers, copies of these papers, and go ahead and read through them and see. Now you're going back and reading a lot of the old literature, and there's a group of abstract papers in there, like I said earlier, that I gathered from as a result of the papers that were submitted for possible presentation at last year's fall meeting. And you're going to see that people are beginning to catch on. They may not have it all put together, but they're catching on to what's out there, or the layered no crossflow reservoir behavior and its implication. You'll see a couple places where they point out they recognize now why their forecasts were so optimistic before, because they're treating everything as a single layer. You'll also see there's many different types of reservoirs described that without question are layered no crossflow, not just carbonates, or not just the Oklahoma Hugoton or Guyman Hugoton. It's all kind. So I think with that we're going to close the session, other than to get copies of the figure. And we might have some, or if you do the enhancement of the figure, we might have somebody do the distribution. I don't know. Why don't we get an attendance list so I can at least have a idea of how many and who was here? If you pass out a sheet around. Any questions? Right. Well, I enjoyed very much an opportunity to present this material over here, and I think I can read from the faces that there's pretty good